formally start cs345. Hey everybody, and um, I we are making the attempt to make it a live meeting at least once a week, maybe. But I had it's I think the fifth or sixth summer that I am teaching during the summer, and basically I had experience with both only recorded lectures versus meeting in person versus meeting online, and as a rule, people in CS445 tends to like to meet in person, or at least live, and people in 345 sometimes yes, sometimes no. So I'll try to get the vibe from you if you'd like to have meetings live and how many of you in there. But we let the course stabilize a bit. Some people will join, some people will be added, and so on. So we can wait with these decisions. Also, some weeks I might or might not be in town, so we'll can play by ear. You'll definitely have all the recordings, either new recordings or recordings from last year's, if I think that are of comparable qualities. Of course, office hours that will be over Zoom. I'm in Tucson right now, so if there is other people that are in Tucson and prefers to meet, it's great. We can also, if I'm giving the lectures, always fun to have to see live people. As you obviously remember from the epidemic time, online is only that much fun and only that much engaging. Let's have our TA introduce himself. Moi, would you like to join us and to talk to the people, tell about you, tell about your research interests?
Hi everyone, I'm Moin, the TA for this course. Um, I'm a second year PhD student at the CS department here, and currently I'm working with Professor John Kesesioglu on computational biology and algorithms, and I am really looking forward to uh, working with you guys this summer.
Fantastic. And yeah, let's talk a bit about the bureaucracy. First, these recordings are completely optional. You can, oh, this the online meeting that happens today is completely optional. If you'll see the recording instead, it should be just fine. Um, though I can speak on and on about, hey, I study much more when I'm participate in live meetings versus Caesar recordings. Maybe it's applicable for you, maybe not. For the same argument, if you want to keep your camera on to see each other, fantastic. But no arm twisting, no penalties, no strict rules. But and for me, when I give the lecture, it gives me the hint of, hey, people understand, your body language, your eyes tells me that it makes sense, it doesn't make sense, what I'm saying. Let's talk about bureaucracy. We will have about 4 or 5 theoretical homeworks, meaning theoretical, you don't need to implement anything for them. And they'll be about 10 days apart from each other during the semester, 4 or 5, and you have to print them, for example, via LaTeX, for example, via Microsoft Words, Google Doc, other things, other options. And that's the first year or the first semester that I actually insist on having the homework typed and not handwritten. It was optional in all the 20-something semesters, that 20-something years that I taught so far. Why do I insist about it this time? Well, ChatGPT, obviously. Oh, you cannot see my mouse. It's need to change the OBS settings, but I will not do it in real time. So theoretical homeworks needs to be printed, and you cannot submit them in pairs. Each person should submit his own homeworks, obviously. Homeworks, you'll see it in the Google Doc. Homeworks are submitted via Gradescopes. You will be assigned into Gradescope, obviously, when we'll get closer to the homeworks submission. And at the end of the week, or early next week, I'll assign the first homework, and the deadline will be 8 or so days after. What about programming homeworks? We will have 2 or 3 implementation homeworks, and the environment will be processing. Check out processing.org and download it and start playing with it. And it's kind of like Java, so your Java will tell you almost everything you need to know about processing, but it's a closed environment. You can work in the ODE of processing only. And why don't I just use standard Java? Well, processing was developed especially to make visualization very, very easy. Again, processing was developed to make visualization interaction with graphical object very easy. Now, the homeworks that I prefer to give you will involve data structures, obviously, because that's really what this course is about, implementation of data structures, most of the course. But it's much more fun to see things happening. And I'm coming from computational geometry, so previous homeworks had to do with points and segments and finding intersection between segments and creating quad trees that essentially you need to place points with your mouse, and there is a data structure that reacts every time that you add a point, and processing just reduces the overhead of getting graphical display to really, really bare minimum. Because write extremely short images, short programs that takes the mouse coordination and do things with it. So it doesn't help for the data structure, but it very, very much will say you can debug and develop and get a feeling of what your data structure algorithms is doing by graphical input output, which I think makes it much more engaging than show graphs, displays, anything else. It's not the only way to process it, to get the graphical course, but it's a way, and it feels, from my experience, the 4 or 5 times that I have taught this course, it's a very, student seems to like it very much. So processing, which is in Java, it's built very much on Java, but there will be an hour or two that you'll spend on getting used to a few different designs. Processing is less elegant about sliders and bottoms. That we will give you different libraries if you want to have sliders, bottoms, read from a file, reading strings. That's less elegant. That's where you need different libraries. If we'll give you templates that just you'll plug into your program and handle this part. It's formally in and out of the processing. And please note the wonderful message that we saw from Ellie in the chat. So it was not pre-planned. Ellie, can you tell us more?
I was just saying that if anyone needed help with processing, I could help with that because I TA'd a class in that language. But I don't know, just offering to help if anyone needed it.
It, it's absolutely great, and it will be counted toward the class participation. That's very much. Which class is this? I honestly
um,
did not know.
it was 101, CC 101. It was taught in processing for like one semester instead of Python, and I did like an algorithm visualizer in processing. I think last semester just for fun. So or a sorting algorithm visualizer to clarify. But if anyone needs help, I can help with that.
Fantastic. It was completely unplanned. Uh, Great help. Thanks. Okay, that would be in yeah, that's about the theoretical homework. We will drop the lowest theoretical homework. A bit more. That is lowest theoretical homework is dropped. Note the theoretical, all your the 2 or 3 implementation homeworks, they're all in the game. We are not going to drop among them. That's about a bureaucracy. Any questions so far? Websites, it's kind of confusing. We are using whole array of websites. The main website is a Google Doc that I shared the link to you. I needed 2 trials until it went. I sent you the correct one, but I think that I finally did it. That's most of the homework. That's where I'll change the links to slides, videos if I think that it's needed, that it's not only in the other folders, and so on. And that's also where all the text about the bureaucracy is there. And I hate to be the bad person, but there is the grading scheme. What do you need to do to get an A, to get a B, to get a C, to get a D? And if you'll notice in this website, there is a bad things that happens if your lowest exam is really, really low. Then essentially, bad things can happen. Try to check the Google Doc to see exactly how bad should you do in the homework that I'll get. That it's just how bad should you do in the final exam in particular, that I'll feel convenient to give you a B rather than an A, or a C rather than a B, and so on. Hopefully it's there just to make people uh, not to give up towards the final exam. So that even that is takes the final exams pretty seriously, even if you did very well until this point. Now, that being said, there is a good side that essentially it goes like, and I'm sorry that I don't have the number right in front of me, but it goes like 15% for the midterms. The numbers might be wrong. 15% for final midterm, 15% of final, and 12 for the max of mid and final. The numbers actually are higher, but essentially what I'm saying is that I look at both these exams, and I look at the better of the two, and I give much more weight to the better of the midterm and the final, and much less weight to the lower among them. So your final cannot be ridiculously bad, but if you did much better in the midterm than in the final, the midterms takes more room. I'm taking the philosophy that some students are struggling at the final because of other courses, but you did very well in the midterm. That's great. Alternatively, you were struggling during the midterm, but you kept yourself together, did great. In the final, then the final will get much more weight. Okay, I think that summarize. And first homework, I'll probably end of this week, early next week. First homework will be out and will be due a week later. Okay. Um, let's talk a bit more about ChatGPT, or actually, yeah. Let's talk about homework and collaboration. In the theoretical homework, even though you are expected to submit them individually, uh, do meet with your peers, think about the question, think about the solutions that you have in mind, and run them on each other. It's a great preparation for the midterm final. It's a great way to study in general, to get practice for real life collaboration, all is good. But then after you have a good idea about how to address so what do you think that the solution should be, uh, if you want to be honest and according to the code of academic yada yada, go home, write everything by yourself from your memory. You cannot copy anything written. Why? Because I want you to understand the main idea. Go home, write a solution in your world where, and if you are able to reconstruct to understand the solution completely, then you probably understood everything that I was hoping that you'll understand to get a solution. Right. So again, brainstorming in small groups is great. Brainstorming with ChatGPT, kind of borderline. Run your ideas, run the questions, maybe on ChatGPT, etc. With or without my permission, borderline cheating, borderline brainstorming, but take into account that the answers that I expect from you might be different than what you'll see from ChatGPT, especially that I'll make a decent, honest effort to make the answer somehow different. So some questions may be deliberately, some are not, but I have no commitment that, I mean, what I'm trying to say is that if you cut and paste the question into one of the available online resources and cut and paste the solution to the homework, we'll probably will find out that you are not honest, and it probably will not be the correct answer, and probably even if it is a correct answer, we'll be able to check it to which extent we'll get for it. That's different, but and on top of it, I'll take example from cs345 algorithms. There is the edit distance algorithm, which is a very common algorithm. There is Frechet distance, another algorithm that uses dynamic programming, both that I'm teaching, and the version that I'm teaching for whichever reasons is different than the version that the textbook, main textbook, will show under Frechet algorithm in general. So you'll get different answers, and that's not even trying to fight against the other resources, just because we teach that differently. And on top of it, if we'll get an answer that, how they said, if we'll get an answer that is very detailed, maybe with pseudocode, but answers a different question than the question written in the homework, it raises some flags that maybe it's not entirely honest on about that if you were not even able to check that the answer that you got from other resources is not really the appropriate answer, it's really a red flag. So whatever you do, make sure that you fully understand the answer, make sure that you fully read whatever you are written. And it's not hard to notice when I see homeworks that are not falling into it. Yeah, that was enough about being the vicious person in the room. Yeah. other line from this slide, you are welcome to share. Well, in your code, there is an interface how to display, how to get mouse coordinates. That spaces share with anybody. The parts of the code that have to do with the data structure is what you are expected to develop yourself. Inserting, deleting objects into various trees, you have to write it from scratch. Okay, let's talk about analyzing discrete structures. Why, how? Here is a wonderful quote that I like: the data structure algorithms frozen in time. You know, the famous take of over art and architecture, I think. So it's nice to say it or not, and that's what we'll do mostly in this course, talk about data structures. We so are data structure and algorithms the same thing? Not exactly, but close enough. We need the data structure that is what happens that the algorithm has created. That is, the search tree is created by an algorithm that insert and delete objects from the search tree. Or in other words, algorithm calls and data structure calls are not really distinct and not really not fully overlap. We will talk about data structures that sit in our main memory, but and probably your secondary memory on your desktop is some kind of a solid state device, some type flash memory, and all of them has interesting behavior that actually influence our algorithm much more than what happens in our main memory. Even if you have a pretty powerful main memory, the more your algorithm starts to slow down when the amount of memory or a good reasons for our algorithm to perform poorly is because you're using the secondary memory and this type access to the secondary memory, God forbid if it's mechanical disk, but in particular, you'll see that they write something into the secondary memory or read something from secondary memory is way, way slower, even in the case of SSDs, way, way slower than reading it from the main memory. So we will talk about B trees and R trees in this course. B trees and R trees. B trees would be a one-dimensional trees for keys and names and numbers. R trees will be a geometrical analogous that works with shapes and segments and boxes and cards in higher dimensions, and all of these ones are doing very well on your main memory but are also tailored to handle the special nature of writing things into secondary memory. What basically guide writing things into the secondary memory is that we are writing it in big chunks. We take big chunk from the main memory, write it into the secondary, and vice versa. And this type of hops takes lots and lots of times. Yeah. Okay, avoiding the. So no, homeworks are supposed to be typed. No handwriting because of, I need to be able to take a piece of the text and copy it. If you want figures in the homeworks, hand write them or create them any way you want. I don't care about figures. No need to type these ones. But the text itself needs to be typed. In what you're submitting at the homework, what you'll submit to Gradescope is just a PDF. So how do you create the PDF is entirely up to you. But it should be a readable text. That is, don't. create a PDF by taking an image, look at the JPEG, and make it into an and submit and make it into an image. I should be able to cut and paste pieces of the text. Let's talk about syllabus. We are going to rediscuss big O and omega and thetas, and to highlight these big O's and omega and thetas, I'll have a set of toy examples that I, I'll refer to them in the homeworks, and they are not appearing in any textbook to the best of my knowledge. It's stuff that I'm carrying with me through the years. And they'll highlight O omega theta, and we'll get to them quite soon. We will talk about proofs, for example, what consists the proofs by inductions. We will talk about recursion formulas that are not actually listed here, but are contained. We'll talk a lot about sorting. Start from swap sort, just replace elements if they are in the wrong orders, via insertion sort into merge sort, quick sort, and we'll talk about a lot. Quick sort is a huge topic that we can go deeper, shallower in the math of it, and it brings us into the beautiful power of randomness. Quicksort essentially will tell you you don't know what to do, toss coins correctly, but let's you have a great karma in life, just let the randomness tells you how to dictate the sorting, and we'll prove or hand wave why this is the best choices that you can do instead of trying to have a deterministic algorithm that always does the same thing. Randomness is fantastic part, and we'll see a few cases of randomness in this course. Does anybody knows about another type of randomness that is very much used in data structures? Now, you might know about two other.
Hashing, right?
Hashing would be one of them. What do we when we have to store a set of keys? As long depending which operation we need to do all these keys, but essentially if we are not sure, let's take some big constant a. Don't need to copy it right now to understand it right now. We'll talk about it much more, but take a big constant a. You have a key k, multiply this big constant by k, you got some number, do modulo the table modulo m, where m is some table size, and make it an integer probably, so it will turn out to be an index in your table. But what's so special about this strange constant? That it's strange. That it tries to destroy anything, any structures that you had in the keys originally. So if you're putting them in a set of cells in a table, they will spread nicely between the cells and will not accumulate in one particular cells. Even if there is structure to start with, the randomness will destroy deliberately, try to destroy this structure. That's the beauty of it, that with hashing we can prove some of this proof we'll see in this class, some will wait for 445, but with hashing the beauty is that here is a way that with high probability, because I'm taking a strange structure, that for almost any set of keys, unless you know what is this constant that I had in mind and you are writing, especially data that tries to get me to fail, but if you're just generating them, even if they are not evenly distributed, even if they are all multiple of 5, all ending up. I'm sorry? So we'll discuss it more, but essentially the hashing would be I take responsibility on me on creating the randomness. Even if my data sucks and all the numbers and the set of keys that I had in mind, or the set of keys that I'm going to insert, is 5, 10, 15, 20, 25, 30, I think that you see where it's going. Even if these are set of keys that I'm going to insert and they are very well structured, and all I'm doing is just taking even just modulo of take the key, take k, and do modulo the table size. If you'll do modulo of 5 as a hash table, then all these keys will be hashed to 0, and that's a very bad idea. Suddenly, all my keys are all mapped into one cell of the table. But if instead I'll take it to be modulo a random number, suddenly things appears very nicely, even if the keys are terribly distributed. And by controlling these random choices that I'm making, not the input is making, I can guarantee against almost any data. I can say that as long as my keys are not chosen by very malicious adversaries, hashing will do very well. Other data structures that you might know that use randomness. Well, that would actually be pretty early in the course. We will talk about skip list. And which are data structure at which are doing way better than search trees, almost always, way easier to implement, way easier to handle, give you almost, in many cases, much better performances than AVL trees or 2-3 trees or B trees, and are just doing great. But you need to toss coins. And you need to prepare yourself that there is some extremely small but non-zero chance that they will not work well. That's another case of structure. That would be the skip list. And along the way, we'll talk about lists and stacks and queues, very elementary data structures, some other abstract data structures. Of course, we need to cover all the search trees. What are search trees in general? Everything that starts by, for example, by sticking a key, say 17 in the root of the trees, and this will tell me that all the keys in my left subtree are all smaller or equal than 17, while all the keys in my right subtree are larger than 17. So, for example, in my case here, 18 and 20 and 100 will all be in the right subtree, and in the left subtree will only have keys that are smaller or equal than 17. How do I arrange the keys in my right subtree? Well, I'll build this all keys recursively. Do I just insert them as they appear, or do I do something actively to balance this tree so the height is not very bad? It's up to you, but we'll study techniques of either do a balancing that will guarantee that the height of this tree, the height, age, the height would be order of log n, and is a number of keys, and the height will be logarithmic, and we sometimes can guarantee it, like in the case of AVL trees or 2-3 or B trees. Sometimes we will prefer to let the tree balance itself, like in the case of splay trees that in practice works great and sometimes much better than just binary search trees. We'll talk about them. Or sometimes we'll just assume that we never do something actively to balance these trees, and it just happens nicely. B trees, by the way, will say, hey, there are too many keys, I don't balance it, I'll split or merge nodes, and this way I'll control the height of the tree. People, any questions so far? Uh, okay, is the sound in Zoom terrible or just mediocre? I don't think that my CPU is working too hard, so Zoom shouldn't be. Let's make sure that my Zoom input.
Yeah, you sound okay for me.
Is the Zoom sound better? I'm now taking the sound from the microphone directly, not from OBS.
Yeah, now you're kind of.
Okay. Okay. And then lots and lots of algorithms. Okay. Thanks for telling me. And then we'll talk much more about graphs, algorithms, graphs. You know, people, Facebook. Uh, I have to show how old I am. Talking about Facebook. Facebook graphs. Here is node 1, V1 will be one person, V2 another person. If these two people's friends each other, there is an edge in the graph between them. If V1 followed V2, then there is an edge between them, but this edge is directed. It says who is following whom, and there are lots of such nodes in this node, and there are a lot of edges, and we'll study things like represent this graph in a way that your computer likes. How would your computer read them nicely? Or we'll talk about this graph and ask how can I make sure that I visit all the vertices of the graph? How can I ask what is the shortest path from V3, the other V3 prime, to the original V3, what is the shortest path between them? We'll study some algorithms here, and other algorithms are taught in 445, depending on what type of graphs they are. We'll ask, is this graph connected? Meaning, is there a path from every node to every other node? We will ask how to find a skeleton of the graph, in the sense that I want to just keep as few edges as possible, but still keep the graph connected. Why would I want to do all of it? Well, maybe because the original graph, maybe what you see as the original graph, every edge right here represent a suggestion of a road to be constructed. Every edge is a suggestion, should I construct this edge or not? And if I'll construct a road from this node to this node, it will cost me $10 million. And if I'll construct an edge from this one to this one, it will cost me only 3 million, and so on and so forth for all the edges. And I essentially don't want to create all the roads out there. I just want to create the minimum set of edges, but I still want to keep my graph connected. So if I have this edge that costs 3 million, and this edge that cost 5, and this was 3, and this one that costs 10, then maybe the one that costs 10 million is not really needed, because if I need to go to V1 from V10 to V1, it's okay that I'll go from V10 to V3 and then to V1, and I don't need to pave this very expensive edge. Similarly, you see that to go from V3 tag to V3, there is I don't need this edge, because if I have it, I do have a cycle. So there is some redundancy. Maybe I want this redundancy, but if I don't, then Prim algorithm will tell us how to construct the most economical graph that is still connected. Out of all the proposal of roads to be paved, how do I stay with just the cheapest one? Why study algorithms in performances? Great question. Well, performances do I care about n algorithms that run in order n or algorithms that runs in n squared? My computer is so fast that it hardly makes a difference. Yes and no, because in many cases it tells me one algorithm is better than another. Don't don't hire him, hire me, because my algorithm is essentially faster. Something about the algorithm. It's not that I ran my algorithm on a faster computer. It's not that I use C rather than Java, and that's why my input code is faster. It's because something inherently about my method is better than the other method. That will give us a way to compare one algorithm against a method to solve it rather than the exact implementation, because the exact implementation is influenced by which computer, implemented by which compiler, and so on. So it's kind of giving us a language. It also tells us more about what can I do in reasonable time, what can I not do in reasonable time. We all know about NP-hard problems. The best definition of NP-hard problems that I know of is you can write a program to solve the problem, but you will not live long enough to see this program ever terminates and give you the solution. So in this aspect, your program is useless if the running time is asymptotically too high. And then we get into the question of asymptotically too high about what? About the worst case, about the average case, about the best case, and so on. So to keep things simpler, we'll usually talk about the worst case running time, and we'll usually talk about the big O notation that you'll probably have seen in other courses, but I'll refresh it very soon. And we'll see a lot of such big O that might be important, and they are important both when we are talking about the CPU running time. They are very, very important when we'll talk about memory constraints. Some algorithms, like very typical for dynamic programming, even if you just have n items that you need in your data structure, then dynamic programming will take n square memory or n cube or n to the 17th times memory, which essentially render your algorithm useless on any big data, even though running time is not really the key component. You are willing to suffer the running time, but you just don't afford much memory because you need, in certain cases, exponential space, not immediately exponential time, but you just to get to the optimal solution, you need exponential space. Sometimes we'll talk about I/O, how many read and write operation we need. Sometimes we'll talk about GPUs or parallel computers, and we'll ask how many parallel steps are needed to solve them. Not in this course, but quite important, talking about how many steps of your GPU, assuming that every pixel, every processor in my GPU is quite efficient, but I still need, even if they are all running parallels, it will still take this much time to solve the question. Okay, and big O essentially tells you when it is reasonable to actually solve a problem optimally, when do you have a chance to get to an optimal solution, and when should you look at, and it will tell you what is a bottleneck of if your code has multiple pieces. What is the most expensive one? Where is a bottleneck of the running time? Sometimes, I mean, note that you cannot do it by with other tools, but sometimes a bottleneck will tell you, and then you need to decide what are you doing instead. If I cannot afford or I cannot live long enough to find the optimal solution, what do I do instead? I can shoot for heuristics, just what makes sense as a reasonable solution. Sometimes we'll shoot for approximation algorithm, but approximation that will say it comes with a guarantee about the running time. Maybe to find, let's be a bit more specific. If I have a network, here is my graph over here, and I want to visit all the nodes, and every edge has some weight with them, and I want to visit all the nodes, and do I have the shortest path? One of the very classical problems to be NP hard, known as a traveling salesperson problem, TSP, and it's known that exact solution is, in certain cases, uh, not practical, like exponential time. In many cases, you can find a solution. In many cases, you can even prove that your solution is optimal, but that would not be an algorithm that works for any graph. It's an algorithm that says for particular graphs, I can find an optimal solution, and I can even prove that it is the optimal solution. Other methods will say, you know what, I'm willing to go twice the optimal path that visits all the nodes, but I want to have a solution really quickly, or maybe only 10% more than the optimum, and I can prove it. Integer linear programming, another topic that I cover in 445, is another solution. It sometimes you can phrase it, sometimes it runs quickly enough, sometimes not, but it's a convenient tool to have in your arsenal to address problems that you cannot run in polynomial time and find the exact solution. You can always try neural network and hope for the best. Sometimes you can write an optimization problems, an optimization function, cost function, look at its gradient, and now iterate improving your solution at each step, and so on. These are all possible options that you have to do in the case that I cannot afford the running time or the memory constraints of exact solution. Let's remind everybody what is a big O, less important and let's start seeing examples. Here is an pseudocode that finds the minimum element as a maximum element, the minimum element in an array. And it's just to get everybody on board in terms of the notation. I'll have an array, here I'll represent as A from 1 dot 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 to N. And I set M. Give me a moment to get to play a bit with OBS, and then you can see my mouse. Or not in real time. M is set to be the maximum element in the array, and now I iterate over all the elements in the array, and for every element AI, if AI is smaller than this value M that I have in mind, then I'll set M to be this new value. And then at the end I return M. That's just an example of a pseudocode, one possible option, because many times I'm faced a question about what is a legit pseudocode, and there is no really an answer for it. Or what is it? It's a sequence of steps where a programmer can, it should hold that a programmer, somebody else can take your pseudocode and make it into a real code without understanding anything about what this code trying to do. But it's you know it when you see it. It's a legit pseudocode if you think that it's a legit pseudocode. Sequence of steps, well structured. Each one, it's clear how to replace it with a real piece of code like a while loop or for loop and so on. And we return. Okay, now when we have it, let's talk about the problem of sorting, which will be another typical example that we will play with. Our input will be a set of keys, a set of numbers, and the output should be some permutation of these numbers. Uh, Alex, somebody was trying to speak. So, and the output should be rearrange these keys. As you all know, your input is 17, 3, and 19, and your output should be 3, 17, and 19. The same keys, just in the order. So A1 is smaller than A2 is smaller than AN after this permutation. And one of the purpose about this slide is to introduce what is sorting and to remind everybody what is a permutation. Now, when we have it, let's talk about one particular algorithm that takes an array and performs sorting for us. How does this code work? For I goes from 1 to n, for j starts at I and goes all the way to the end of the array. What should you do? If ai and aj are in the wrong order, then you swap ai with aj. Not surprising, right? And we can ask what's the running time of this array. So, or how can we prove that what we are getting from the array is actually sorted? And to prove that the algorithm does what it's supposed to do, which is sorted, we introduce the idea of invariant. Invariant will mean some statements that is always true at every step of the algorithm. Invariant, a statement that is always true. It takes a proof, but we can prove that this statement, written in the middle of the slide because you don't see the mouse, this statement is true at every step of the algorithm. What is invariant in this case? That all the elements after the ith step for every I, after the I steps, all the elements from A1 all the way to AI, these are all sorted. What happens with the rest of the array, all the way from I all the way to N? No claims about it. No argument that it is true, but we can prove that this statement is true after the ith statement. What's the running time of this algorithm? Well, the running time, let's think about it. The running time would be, please pay attention, for the to the end of the slide. What happened when I equals 1? When I equals 1, j goes through 2, 3, 4, dot, 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 all the way to n, which takes altogether n steps. For I equals 2, j will go through the values 3, 4, 5, all the way to n, which takes n minus 1 steps, and so on until I equals n minus 1, and then j go through the values n only, and then it stops. So what's the overall running time out there? It would be order of, and we'll be more formal about it, but it will be order of what? It would be order of n, that's when we start. It's actually n minus 1, but we don't care, and we'll talk about why we don't care. N That's what happens for I equals 1, plus n minus 1, which is what happens for I equals 2, plus n minus 3, plus dot dot dot, all the way up to 1. What does this sum equals to? What's actually written here? Let's read what's written here, but now let's read it from right to left. Let's read the sequence from right to left. It's order of 1 plus 2 plus 3 plus 4 plus dot 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 n. What's written here? Hey, I know what it is. Let's remind me something from that's just a it's a series, that's a sum, and it is an arithmetic sum. And
Natural numbers 1 to n is n times n plus 1 over 2.
Exactly. So that's just because it's arithmetic. Sum has a formula n times n plus 1 n plus 1 over 2. There are too many characters here for my pleasant. I don't like the 2. I don't like this discussion about is this plus 1? Is this minus 1? I keep getting confused. Well, that's the beauty about the big O. Big O, as we'll see, helps us just decide, you know what's really the dominant part in all this expression, n times n plus 1 over 2. What's really dominant here is that it's n times n, and everything else is just noise. Order of n squared is what really dictates the running time of the algorithm, and if it's plus 1 minus 1, doesn't matter. So the big O is kind of a lens that we can look through it and say, what's really dominant about the running time? What makes this algorithm slow or fast? What's the bottleneck of the algorithm? Well, it's a n times n. It's essentially behave as a order of n squared, quadratic running time. So let's remind or tell you what is order of big O. The statement is really, really confusing. For me, it takes ages for me until I started to feel comfortable understanding what it is. So what a big O is it's a legal statement, which is a shorthand. When I'll tell you the T of n, the running time of the algorithm on n items, if I'll tell you that the running time T of n is order of G of n, usually order G of n, this function here in this between will be one of the following. N all the time, in most cases, n will be the input size. How many elements do I have in my input? I'll tell you that the running time T of n is sometimes order 1, which might or might not be a correct statement, but it is a statement. Sometimes I'll tell you that the running time is order of n log n. So in this case, G of n is n log n. It's a statement that might or might not be true for one particular algorithm. It might be order of 2 to the n for one particular algorithm, and so on. But depending on, I'll say the running time is order of T of n. What do I mean by writing it? It means that I can find some constant, I can compute, or I don't show you right now, but if I'll be in code, I can show you an exact values of constant, namely C and N0, such that, to make this claim true, I can show you these two constants such that T of n, the running time, is small or equal than C times then this constant, the first constant, times 2 to the n for example. Is this true for any possible n? No, only for large n, only when it starts to matter anything. And this should be true only for large enough n. What do I mean by large enough? How do I decide what is small, what is large? Well, I don't need to show you right now because I told you that t of n is order of 2 to the n. Then I don't need to show you what is the constant c0 right now. And I don't need to show you what do I mean as meaningful constant, this n0, but for every n that is large enough, t of n should be order of 2 to the n if and only if I can show you this constant such that t of n, the running time, is smaller than some constant that I can show you, of course non-zero, larger n positive, times 2 to the n. Back to our sorting algorithm. Is it true or false that t of n, the running time, is order of g of n? True or false? The swap sort that you see at the top of the slide. True or false that it is order of 2 to the n?
So it's n squared.
Sorry?
N squared.
You said,
It's false.
uh, so of course it was a very cheap example of a cheap answer. It is true that the running t of n is order of 2 to the n. And in this aspect, telling you about something that is order, big O, is completely misleading. It's like the old example of you are in a balloon. It's a correct statement that may be completely meaningless, but it's still correct. It is true that the running time of the swap sort is smaller than 2 to the n. All I need to show you is that it doesn't take more time than 2 to the n, which is true. It's actually, I can find a much more meaningful bound. For example, I can say, hey, it's only n squared. I can even say it's only log n, except that that will not be true. It will be more than log n, but not more than 2 to the n, yeah, and so on. Like, we will actually study a data structure. That's where we will get to the big omega. You're absolutely right. To make it, if I want to, big O is tell you, hey, don't sleep about it because it will not run in more than 2 to the n. Maybe it will run much faster, but I can prove that it will not run in more than 2 to the n. Probably 2 to the n is not something to write home about, but if I'll tell you, in this case, that t of n is order of n squared, which is a correct statement because the calculations that we did earlier told us that t of n, the number of steps, the running time on n elements, if you remember, the number of steps was n times n plus 1 over 2, which is order of n squared. Hey, what about this constant c that I just wrote here? This constant that I can prove. What does it let me state? The fact that there is this constant just tells me, allows me to talk about number of steps as if this is the actual running time. Because I'll assume that in 1 second I'm doing a constant number of steps. So if you're talking about steps or you're talking about running time, as long as every step is just a constant operation, we don't need to specify what is exactly this constant. People are happy? Understood why it's true that t of n is not more than 2 to the n, which implies that t of n is order of 2 to the n. In the case of sorting, again, if you have n items in the array to sort, then the times it needs for this swap sort to sort them is not more than 2 to the power of n times this constant. And actually, it's true for the swap sort that T of n is order of n squared. That is, T of n is not more than a constant. Which constant? I don't know, I don't care, times n squared. By the way, hopefully the image and the fonts are large enough. If not, then switch in your Zoom to a speaker view. Yeah, and then hopefully the fonts are large enough. So what will be g of n in the general? It will be usually order of 1. It just means, hey, I don't care about the input size. For every input size, my algorithm takes a constant time. Probably this algorithm doesn't do a lot of things, but sometimes it's meaningful. Sometimes it will be log n. Many cases we'll see that insertion into a balanced tree is order of log n. Deletion from a balanced tree will be log n, and so on. Log square n, another example, order n, example, finding the minimum in the array, finding the minimum, the code that we saw 10 minutes ago, find min takes order of n, not more than n steps. N square log n, another type, exponential will be maybe next one, and so on. Graphically, it will mean, look at this graph on the lower left part, that if I want to tell you that the running time is order of g of n, for example, order of n squared, what does it mean? Here on the y-axis, I will write the running time on n items of the swap sort, for example. On the x-axis, I'll write n equal 1, 2, 3, all the way to n. And here is a graph of here is a graph of t of n. And by telling you that t of n, let me redraw it so to be consistent with the slide. Here is t of n, and if I want to argue that it's not more than n squared, it's just a shorthand of telling you that, hey, I don't care what the running time is for very small n, don't argue anything, but there is some number n0 for which the red graph t of n is not more, is bounded from above by n squared, but I keep the freedom of multiplying this n squared by some constant. Maybe I need to, maybe we are counting it by years instead of milliseconds, so I'll multiply by the appropriate constant. People, questions so far? And again, be generous with yourself. It takes lots of time before you. If it happens, if you have not seen it in previous courses, it takes quite a while until you'll find convenient with this. Again, order of n squared, it's a legal statement. I can generate this constant if I have to, but I prefer not to say it specifically. So I can say that the running time of my algorithm is order of n squared. I actually saying this very long and tedious sentence. I could show you, just ask a constant c such that the running time of my program never exceeds c times n squared. With another disclaimer, I don't make this statement for every n. I make these statements only for large enough n. And I keep the right to tell you what is this n squared, what is this constant n0 that I'll call. That's where the size of the input starts to matter. But on small inputs, any algorithm will run fast. Who cares? Only for large n, I really care. Okay. So usually T of n is a running time and n is a input size. Okay. Does it mean that I'll never use n cube algorithm instead of n square? Obviously it's not. Does it mean that I'll never use exponential running time instead of, well, no. 99% of the problems in the world are NP hard or harder. You cannot only shoot for problems that are have fast algorithms because they are a huge minority of the problems, and that actually can be proven. But it tells you at least that keeps your expectation low as far as the quality of the solution that you'll get. That is, you'll have to settle for type of approximation of heuristic, or it sounds good or it's good in all the cases that I've seen, but I cannot prove maybe optimality. Okay, it's a useful tool to ask. That's something that I can and should obtain. The exact solution, the exact sorting an array is simple. Finding TSP, much harder. Okay, let's play with some of the examples that I had in mind. Here is a snippet of code that are called no need, and what no need is doing is read an input n and start from j equal 1, as long as j is smaller than n, increment j by 1, and print a star. Each step, print a star, an asterisk. How many stars will be printed? Not too hard to check that in this case. You'll print n stars. So the running time, assuming that printing one star takes a constant time, then printing n stars will take order n time. Right? Constant times n is, in this case, is the parameters that you read. In general, it might be the input size, not necessarily. Okay, why do I so by saying that T of n is order of n, I want to tell you that actually for any well, what happened when I just call this function? It takes some time to upload it to the memory. It takes some time to clear the stack of to the stack of which function calls which. There is some initialization cost. Don't care for it, but for any n after it, as n increases, behavior should be linear. Right? You double n, the running time should be doubled. The graph, the asymptotic running time, should behave as a linear graph. Or I can tell you that T of n is not more than 3 times n for every n. No, because there is this big overhead at the beginning just to call the code. But after I call the code, then the running time is not more than 3 times n. So is this example clear? Okay. And again, I assume that many of you have seen it before, so just quick refreshment. And again, these examples that I showed you, it's not taken from any course as much as I know. Here is another piece of code. No need of n, reading a number n. For j equal 1, j is smaller than n, do j++. For k equal 1, k is smaller than n, do k++, print a star. How many stars do you say? I'm saying star just because I don't know to pronounce asterisks correctly. Or how do you pronounce this font, this symbol? Leave my monster alone. How do you pronounce this? Asterisk? Asterisk? Asterisk. Thank you. So nice to have a kid available around. Leave my monster alone. I'm in class. How many stars are printed? Well, look at this code. Here I start at k equal 1 and I go all the way up to n. So for every value of I print n stars. So altogether we are printing n squared, many asterisks. So T of n, assuming printing an asterisk, a single asterisk is 1. it will be an at most, or bounded by t of n is no more than 17 times n squared. Why 17? Because in this course we have very, very little respect to constants. All the constants in this course are equally valuable or unrespectable for us. One constant is just as good as another. We don't care about what this constant is. Sometimes it's practical, sometimes mostly it's not. But what is this constant? We don't care. As long as there is such a constant and it's not zero, we are good to go. What about this code? No need. Now, in this case, what's the difference from the previous code? No need of n, j star from 1 to n, and now I still let k goes from 1, but k only goes up to j. Now it's true that for every value of I print n star, n asterisks? Obviously not. When I is large, then the number of asterisks that I print is large. And is small, then k can go only up to j. So how can I analyze the running time? Well, once again, we are back to the same summation of 1 plus 2 plus 3 plus 4 plus dot dot dot, and give us once again n times n plus 1 over 2, which is for us order of n squared. Wait. How come it's order of n squared? What happens to the half that I just had over here? That's not respecting constants. Half and 1 are equally good. They are vanishing inside the big O. Okay. What happens here? That's a recursive code now. Read n, and if n is smaller than 1, then return without doing anything. Otherwise, print 1 asterisk and call yourself with no need of n minus 1. That is our first example of a recursive formula. Recursive formula are written as t of n, the running time of n elements, if you wish, will be 1 in the case of n equals 1. Otherwise, it's 1 because it always takes at least a constant. Guys, are you good with reading the font? Loud enough? Can you read the font? Yeah. Okay. If n equal 1, it is 1. Otherwise, it's 1 plus, there is some recursion happens here, t of n minus 1. In this case, you see that there is a call of no need of n minus 1. That's a call that you see out there. And we will see a few methods to analyze the running time of such recursive formulas. And recursive formulas are important in the same way that going to the dentist is important. Like, I guess that some people see some beauties in it. In this course and in 445, you'll have to study a few of the recursion formulas, a few of the methods you're not expected know that I particularly value. Being an expert of any type of recursive formulas that you can have, we'll see a few typical ones that keeps appearing in many algorithms. And this is just the simplest such example. And one way to solve an example of recursive formula is just, let's really analyze what's running time. And to help you analyze the running time, I'm just printing an asterisk every time that I call this function and asking how many asterisks will I print. Because running time is just a constant times number of asterisks. So what will be the running time? T of n T of n is just this constant. What is this constant? Time to print one asterisk, this one that I had before that, plus T of n minus 1. Great. I just ask what is T of n. It doesn't really help me that you tell me what is this case. But let's go one step further. This would be C plus, what is T of n minus 1? It's C plus T of n minus 2. Right? 2C, which is also known as 2C plus T of n minus 2, which is therefore 3C plus T of n minus 3, which equals to, let's guess, k steps into the future. Let's guess what happens after k steps for every value of those k's. Everybody understand where the 3 appears here? The 3 appears because I wrote T of n minus 2, which is C plus T of n minus 3, and this C was added over here. C, the constant that it takes to print, one asterisk. After k steps, let's guess, it would be k times C, because I did k steps, plus T of n minus k. That's true for k equal 1, 2, 3, and for any values of k's that you that you have in mind, as long as this number is somewhere larger than 1. Fantastic. What happens therefore if we are good with this formula? What happens when I decide that k equals, if it's true for any k, what happens when k equals to n minus 1? What happens when k equals to n minus 1? This equals n minus 1 times c plus t of, what is n minus 1? N minus 1 is just 1. And that's exactly my signal to stop, because it's n times c. And t of 1, we had it earlier, t of 1 is just 1. We'll just c once again. So overall running time is n times c. C is constant to print an asterisk, which is, whatever c is, this is order of n, linear in the input. Okay, similar example, but now what's the difference? I read n, and for if n is smaller than 1, for example 0, return and do nothing. Otherwise, print how n star asterisks and call yourself recursively with n minus 1. Call yourself recursively with n minus 1. We read n, call ourselves recursively with n minus 1. Check these slides, but what's happening here? T of n is C of n plus T of n minus 1. What's the big difference between the previous slide and this slide? In the previous slide, C was stand alone. And again, I'll spend the minimum time that I could, and still call you, doing this course, teaching recursive formula. As I said, I don't expect it. It is not a course on recursive formulas. It's a course that needs recursive formulas as a tool to analyze algorithms. And that will be mostly my expectation. What's the difference between the previous slide and this slide? Previous slide we printed one asterisk, so it takes only C time. This slide we print n asterisks, so I need to multiply the C by n. Multiply the C by n, C times n, plus T of n minus 1, which would be, what's the effect over here? Instead of just C, now I print n minus 1 times C. What about this C? It will be called with n minus 2 such. cs. Uh, sorry, let's get back to the slides, which is do the same iterative substitution, and you're ending up with this formula that we are discovering in the third time today, which is c times n plus n minus 1 plus n minus 2 plus dot 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 1. Hey, what this formula equals to? It's very confusing when we read it from left to right. So let's try reading it from right to left. From right to left, what do we get? 1 plus 2 plus 3 plus 4 plus n minus 1, n minus 2, n minus 1, n. 1 plus 2 plus 3 all the way to n, all of it, times this constant that we don't know what and we don't care, which makes it, once again, order of n squared. And actually we'll see that this is theta of n squared, which will tell us, we'll have to define it, but theta of n squared will tell us, hey, not only that it's an upper bound, but it's actually also the lower bound. That's up to a constant that's exactly the running time, no more than n theta, big theta that you see over here at the end of the slide, big theta of n squared is will tell us that it's not only that it's order of n squared, but as Nicholas asked earlier, it's also a lower bound, a tight lower bound. It doesn't take less than n squared to run this code. See a question in the text. The c constant here is the time that it will take, say, to print an asterisk or to call this function. It's a constant time. What is this? I don't know, I don't care. But I know that there is such a constant that it takes my these many core device to print a single star. Okay, so it's just an arbitrary constant. What's the beauty about it? It all vanishes in the big O. Okay, that's actually this almost the same recursion. Let's skip these slides. Next. This is an example that will repeat so many times in the course. So pay attention to this example. Read n, k is 1, and as long as k is smaller than n, do k equals 2 times k. K equals 2 times k. As long as k is smaller than n. What's the running time of this code as a function of n? Well, we know that one iteration takes constant time, c time, c, a constant that we don't know, we don't care. Yes, you're absolutely right. I let something grows in exponential rate, and I ask how many steps of this exponential rate I have until I filled the whole input of size n. But yeah, let's go slightly slower. What will be the values of k? So k here will be, at the first iteration, k will be start with 1. That's a 0 iteration. Next iteration, k will be 2. Next iteration, k will be 2 times 2, also known as 2 to the power 2 to 2 squared. Also known as 4, but I prefer not to think about it. Next iteration, it will be 4 times 2, making it 2 cubed. And essentially at the ith iteration, or after many steps of the code, k equals 2 to the I. Agree? K equals 2 to the I. It's true for the 0 iteration before I did anything, then k was 0. 2, 1, you know, is 2 to the power 0. It's true after the first iteration, then it's just 2 to the 1, 2 to the 2, 2 to the 3, and so on. K equals 2 to the I. So that's the time to remind you a few formulas about log. Log, no matter in which base am I using it, could be base 2 or base 10 or base e. Log of a times b, log of a times b is log of a plus log of b, I mean the part in this box. Log of a to the power of b, again, doesn't matter what's the base of the log, but log of a to the, when a to the power of b, you can always take this b that is written right here and move it to be before the log. So this is b log a. Okay, and our third formula is that log to the base a of some number x is log to the base of another number, say a is 10 and b is 2, log to the base b of x times a constant. What is constant? We will usually would not care. It's log to the base b of the value of a, but usually it will just be a constant, which is as much as we care about it. Now, when we have the three formulas in our arsenal, let's get back to analyze the running time. What do I know that is true after the jth iteration? After the jth iteration, or if j is the last one, I know that for any iteration, k, after any iteration, k is still small or equal than 2 times n. It's true for any iteration, including the very last one. In the last iteration, as long as this loop going on, and as long as the while is true, the condition of the while is true, then k is actually smaller than n. And how large can k be when I exit this loop? K could be at most 2 times n. So k over here, which is 2 to the j, or 2 to the I, which was k, is smaller or equal than 2 to the n. What I want to ask is how much, what's the running time? So let's ask how many iteration can I have? How many iteration? Well, if 2 to the I is smaller than 2n, let's take log to the base 2 from both sides. I'll take log to the base 2 of this part, log of the base 2 of this part. Log to the base 2 of this part, log 2 of 2 to the I. What's written over here? We said that we can take the I and write it before the log. So this becomes I times log to the base 2 of 2. What is log? What should I write when I write 2 to the power of something equals 2? What is log of this number? What should I write in this box? It's obviously 1. So log of the base 2 of 2 is nothing but 1. That takes care of the left side. What's written in the right side? Small or equal than log, once again, to the base 2 of 2n. Log to the base 2 of 2n, which is log to the base 2 of 2, which is, we just saw it's 1, plus log to the base 2 of n. What did I get altogether, summing it up? I, for every iteration, it's the ith iteration, the value of k, or log of the value of k is smaller than log to the base 2 of n plus 1, and that's true also for the ith, for the last iteration. So the number of iteration t of n, the running time, is small or equal than log to the base 2 of n times the constant. My next step is to think about the log to the base. To get annoyed, I'm really lazy about what I'm writing. Should I write the 2 over here? No, because I don't care what the base of the log. I can always move from one base to another by multiplied by a constant. So t of n is order of log n. Okay, let's see the same amazing result in a bit less obnoxious way, or less irritating way. What is the value of n out here? First, any questions about it? People? Any question about this proof? You will be asked to do similar things. So, but I also want you to get to the same conclusion in a less mechanical way. I'm looking at the while, what happened in the while, and the it's the last iteration. How? Let's look at the last. How many times did I? What happened one iteration ago? One iteration ago, 2 to the, if I is the last iteration, that 2 to the I 2 to the I minus 1, if I is the last iteration, was still smaller or equal than n. Yeah, yeah, j minus 1, thanks. Stand corrected. Yes, so I can, it's a semantic of how do I define the last iteration. So in the last iteration where the while was still correct, yes, the last iteration, then the conditional, the while was still true, k, which is 2 to the I, 2 to the j minus 1, was still smaller than n. If I'll define the number of total iteration including the last one, then I cannot argue that when I'm done, k is still smaller than n, but I can say that if it was a number that was smaller than n and now I multiplied it by 2, then it's smaller than 2 times n. It's the case of the problem with these trivial things is that the more you talk about them, the less obvious they become. Everybody agrees? If we are only counting successful iteration, then k 2 to the j is still smaller than n. If we are including only the one iteration that make k larger than n, then still k is smaller than 2 to z. See, that's one of the beauties of the big O, that in this case we don't care about are we counting this type of iteration or this type of iteration. It doesn't matter when we ask about the order of magnitude. So let's see the whole thing also visually. What is the value of k after when we start? K equal 1. What is the value of k after one iteration? One element, one bacteria, give rise to two bacteria that after one iteration, that's k equals 2 to the 2. Each one give rise to two bacteria, which indeed gives rise to two bacteria, and so on. This exponential goes, and we are asking what should be the height, how many iterations do we need until the number of elements over here, the number of nodes, is at least n, and obviously we only need log many iterations. So it's a toy problem that just tries to remind you or to refresh the working with log. Okay, let's jump between examples and a formal definition. Insertion sort, a bit more sensitive and sometimes more, in many cases actually, much faster than swap sort. Swap sort, remind you, check each and every pair, and for each and every pair, if they are in the wrong order, they swap between them. No, so it will be n square running time for swap sort no matter what, even if you start from a sorted array. Insertion sort try to say, hey, it used to be a sorted array, but then somebody modified but very few elements. Let's try to take advantage of it. I mean, the algorithm will work for every array, but will be significantly more efficient if we start from something that is almost sorted. So what is insertion sort? Insertion sort will, that I use to introduce a few things, is saying the following. It will assume that all the elements from A1 all the way to AJ here is the element, here is my array A. 2, 7, 10, 12, and 5. And what I'll assume in every step of my iteration is that all the elements from 1 until j, this part of the array, will be sorted. I'll assume that for some prefix, let's introduce another word, prefix of the array, this part of the array is sorted. And now I'm checking the j plus 1, sorry, that's actually j minus 1, all the elements until the j minus 1. And now I'm meditating on one new element. Maybe it's the last element of the array. That's the element, the jth element. And I'm asking, hey, can I just replace j minus 1 by j and claiming that the whole array is sorted? How can I check that the whole array is sorted? Well, I know that all the elements from 1 all the way to j minus 1, they are sorted. That's my invariant. That's what I, by induction, assume that is true all the way until this step. Can I just append 5 over here and continue to the j plus 1? Maybe yes, maybe no. If yes, I can, it's very easy to verify it. All I need to check is that is the jth element larger than the j minus 1? Had this been 15 rather than 5, which is, you know, we can prove that 15 is larger than 12, then I just check these two numbers. Given that this is all sorted, plus this guy, fine, it was 15, just add it, don't do anything. But it's not, it's actually 5. If it's 5, then let's continue until 5:10 because we cut a few minutes, and 5:10 and call it a day. Hey, there is 5 here. Now I need, which obviously implies that I cannot assume that everything until here is sorted, so this 5 needs to be inserted somewhere. Arrays is a fantastic data structure. Arrays are fantastic. They are as efficient as you could. They are great when you optimize your program. Compilers like them. They are great when you have multiprocessing or try to optimize your memory when you take a big chunk of memory and move it from one place to another. You can have gizmos on your hardware that can copy pieces of memory contiguous pieces of memory like arrays, very far from one piece to another. Image verification is very fast. They're all great, except what's my problem with the 5? What's wrong with the 5? It needs to be inserted somewhere in this array. An array must be, and this is real arrays, it's not what Java or JavaScript make you think that is dynamic arrays that can have that you can just insert or append elements where your uh, where some nice people arrange the array in a dynamic way. If you want the full use the full benefits, keep it as a continuous piece of memory. But if it's contiguous piece of memory and I need to insert 5 over here between the 2 and the 7, the only way I can do it is by taking everybody right here and move it to the next element. Move the 7 one step to the right, move the 10 one step right. And now I will have the empty place right here that the 5 can go between the 2 and the 7. Make sense? So shifting all these elements would take some time. How much time? Linear time. So what will be insertion, the basic steps of insertion sort? Well, we have all the elements from 1 to j minus 1 already sorted, looking at aj. If aj is not in the right place, then we like the 9 that you see in the slide, then it needs to move backward, which would means to move some elements forward. So I will tell us where do I start shifting elements to the right. Okay, so at the end, after I'll shift elements to the right, I can place the 5 at the right place. Okay, so here is a pseudocode of insertion sort. J is the larger element, so always j is smaller than I. And while j goes from 2 to n, do the key equal a of j and at each time the while loop will never takes this while loop, which might never happen. It happens only if ai is larger than the key, what was a key, equals to the aj. Check out this loop to ask, is this the first time that you have seen insertion sort? Like, have you covered insertion sort in previous courses or not? Nobody said that they did. Okay, so the code tries to be efficient to death, and that's why it's a bit less friendly to understand. All we are doing is the outer loop will continue happily until the inner loop says, hey, I need to shift anybody. Whom do I shift? I shift elements as long as both conditions of the loops will happen. So what the inner loop will do in this case, it will hold key as key would be 5. That's a value that I hold at the moment. And now every element backward that is larger than 5, every element that is larger than a key, larger than 5, need to be shifted to the right. Why? Because we want to make room to the 5. That's why the 2 will not be shifted. But now what happens is 12 would move to here, taking the 5 place, but that's okay because we have key store. Key knows what is that the 5, so we can override the 5. 12 move from here to here. 10 moves from here to here. 7 moves from the second place to the third place. we never move the 2. The 2, we are very happy. We stop the inner loop at this place. And there is now room for the 5. So at the end of the loop, a of I plus 1 will be 5. And now I can ask what happens after the 5th element, and so on. So why is this efficient? Again, it was a loop that just moved as many elements as I could. And if you think about it, if you start from a fully sorted array and you just change one element, then you're done in linear time. Just you change this 12 to be minus 12 and everybody else is sorted, then you'll shift the array always only once. Okay, what is the worst case running time of this code? What's the worst case running time? Oh, let's ask first. What will be the worst input order? The one that will cause the running time to be the maximum. If the array is sorted, then I just need one pass of the insertion sort that essentially just validates that the array is sorted nicely. Exactly. If the array is sorted, once again, but if the array is sorted but in decreasing order, then every element need to be shift. How many steps do I need to shift the 5? I need to shift the 5 3 steps. What about the 3 over here? 4 steps, 5 steps. Once again, we're in our formula of 1 plus 2 plus 3 plus 4 plus all the way to n, which we have discovered so many times today. So the worst case running time is just as bad as swap sort. But it's a big gap between the worst case versus expected or average case, or what happens if the input is, if it's not the worst day in my life and the input and the array is reasonable. So just an example, worst case doesn't mean that it's always the running time. It's much more sensitive than that. Let's talk a bit about properties of big O and call it a day. Let's assume that I have 2 pieces of code. One piece of the code, T1 of n, will be order of G1 of n. Nobody likes big indices, so let's assume that I have one piece of the code that takes T of this space is order of n squared. And when I'm done with this piece, I'm performing another piece, and the running time of this piece is only order of n log n. So again, I first ran my first piece of the code that takes order of n squared, and then I ran the second piece, T2, that takes order of n log n. What's the overall running time? Overall running time, T1 of n plus T2 of n. Well, it is order of n squared plus n log n. But okay, which is in this case, what's more dominant, by the way? It's only order of n squared. So that will be the overall running time. But still it takes a proof. So let's see once how do we do these proofs. And once again, it's not the coolest part of this course. So there's plenty of cool things that are coming up, let's survive through this. If T1 is order of G1, for example, G1 is just n squared, T2 is order of G2, then the running time of both of them, this after the other, is order of G1 plus order of G2. That's a legal statement. How can I prove to you that it's correct? How can I prove to you that this claim is correct? Well, what does the first claim is? What do I mean by saying that T1 of n is order of n squared? It means that when I told you that T1 of n is order of n squared, it's a shorthand of telling you the full speech that there are constant, this notation E backward exists, there are constants N1 and C1 such that the running time such that T1 of n is smaller or equal than C1 times G1 of n. What was G1? N squared. Smaller or equal than, let's say, C1 times n squared. Is this true for any n? No, only for n larger or equal than n1. This constant that I have, that's only what I called large enough constant. So that's true. Go to the proof of the slide. That's true for any n larger than n1. Similarly, for any n larger than n2, the running time of the second piece of the code, the second piece that I had right here, doesn't take more than this other constant times n log n. But the second piece of the code, T2 of n, can you see it? Yeah. T2 of n is smaller or equal than C2, what was it? N log n. What is this C2? I don't know. That's some, I can give you this constant once you'll prove to me, but it depends on so many parameters and I don't want to tell you. But if I knew that the second piece of the code that was here, takes no more than n log n, I can prove to you this constant once you tell me at which unit you measure the time. So that was the running time of the first piece. That was the running time of the second piece. Then what is the overall running time? It's no more than C2 of n. The overall running time, go to the end of the slide, T1 plus T2 is no more, I'm 3 lines from the end, C1 times the first function, G1 was n squared, plus C2 times the second function. But now to prove to you that it's no more than, let's write it down. It's C1 G1 of n plus C2 G2 of n, which is smaller or equal than what? Let's take C1 and C2 and let's assume that C1 is smaller than C2. So let's replace it by max between C1 and C2. If this is a constant, this is a constant, there is a maximum of C1 plus C2 times G1 plus G2. Right? Replace, assuming C1 is smaller than C2, replace both of them by C2 because it's larger, the maximum of the two, times G1 plus G2. Believe me, that's obviously correct. That would be the constant. And this will be true for any n, which is, the first claim was true for only n smaller than n1. The second one was true for any n smaller than n2. As long as I pick n that is larger, than the maximum of n1 plus n2, oh, these ones, let's take it by C1 times C2. Take it back. That would be smaller or equal than the constant C1 plus C2. And this will be true for any n that is larger or equal than n1. And at the same time, n that is larger or equal than n2 So in particular, for any n that's a larger or equal than the maximum of n1 plus n2, or maximum of n1 and n2. What did I try to tell you in all these many letters? That if I have two functions, one behaves as n log n, one behaves as n squared, put both of them together, look at the maximum between these two, that's a dominant term. Big O is a length again that helps you see the important details. Two functions, what takes more time, that's what determines the big O. And let's call it a day. It's good. Questions about it? Check out the details of the proof, nothing in it, and I'll publish today's follow-up of this video with a few more examples and yeah, start and a bit more recursion formulas. Thanks everybody. Bye.